Good morning, everybody. Welcome to RISDA 2018, Day 2. This is the Geoscience Day. My name is Greg Hakim, and as I mentioned yesterday at the icebreaker, I'm thrilled to be here and participate in this school. I'll tell you a little bit about myself in a moment. First, let me give you a sense of what I plan to talk about today. This first lecture will be on an overview, and I did a little data assimilation myself based upon observations I made yesterday on Eugenia's lecture and Takamas's lecture and what I saw Steve Penny doing with you in the hands-on section. I have adjusted some of my slides, and hopefully that will provide you with the third overview of the some of the basics. I'll talk about some main themes, and again, this is particular to the background I have and the problems that I've worked on, so it's not meant to be comprehensive. I can't cover everything, so I'm going to cover the things that I know best, and I'll try and hit those things, thinking especially about students who may be implementing some of these methods, the things that I and my students have learned, and the things I think you should worry about if you plan to use these tools in your research. And then if I have time, I'll talk about coupled atmosphere ocean data assimilation. The second lecture will carry through that theme. I think it's a very exciting problem, kind of stretching the boundaries of data assimilation into paleoclimate data assimilation, where we have to really change how we solve the problem. We're not dealing with instrumental measurements with known air characteristics that are essentially point-wise in space and in time. They're very noisy. They're heterogeneously distributed, and they're time uncertain. And their relationships to the fields we're trying to reconstruct are also highly uncertain. So it's an exciting problem, relatively low dimensional though, so we can start to solve this problem in ways we can't consider for typical high dimensional problems in the atmosphere and the ocean. Then we'll take a lunch break here, and in the third lecture, I'm going to talk about how we can measure the impact that observations have had on the analysis. There's this wonderful set of tools that we get with data assimilation. We don't just get the ability to analyze the state. We'll get the ability to see how those measurements influence that analysis, both in the observation space, which is traditional, and I'll introduce to you today a new way to find the optimal relationships between the measurements and the state variables in a ranked order fashion. And in the final lecture, we'll extend this one step further and look at a sensitivity analysis in the forecast realm, how observations inform upon the forecast, and how we can use data assimilation in the temporal domain to improve forecasts once they've been issued before the next cycle of data assimilation. There's an opportunity there for nowcasting and short-range forecasting where we can use essentially the data assimilation framework to improve the forecast. So quickly, just so you can set expectations about what you might get from me today, I'm a dynamicist, and I use data assimilation as a tool. So I do a fair bit of data assimilation, but it's with a goal of mainly trying to understand problems in dynamics, weather dynamics, climate dynamics, and also because I think it's a really wonderful tool set for my students and my postdocs to carry into their careers. And I think Takamasa made a fantastic point yesterday. This is about scientific literacy, and we hear a lot about big data and those sorts of issues about combining forecasts and observations, and this is what data assimilation is all about. So it gives you a wonderful toolkit. You won't just be a modeler, you won't just be an observationist. You'll have to know about both of those things, now to fuse that information. And I think that makes you a very compelling candidate for jobs in the future, compared to those who don't have those skills. How's that for motivational wisdom for the school?
Maybe follow up later.
Okay. Yeah, and ask questions during the lecture if you like. Like I said, I think I have more material than I can possibly cover, so I'll just get through whatever I can get through. So I'm interested in data assimilation for extracting information from measurements, climate weather forecasts, and really about physical understanding of the system. So for this first lecture, a little more motivation. I'll sketch the big picture. Eugenia alluded to a Bayesian view. I'll do a 1 or 2 slide overview of that. show how, with appropriate approximations, this is consistent with the least squares view that we mainly saw yesterday. I'll talk a little bit about variational searches and direct solvers. You were starting to do the first one yesterday in the practical. Sorry, you were doing this a bit yesterday, and you'll start, no. You did variational searches yesterday, right? 3D VAR? Yeah, and you'll do, I think, the ensemble direct solvers today. And then what you might call lessons from the trenches, these things that you may not find as the chapter title in a book, but these things that you just really need to know, the important lessons for applying ensemble filters, mainly controlling sample error, and things like serial observation processing and augmented state vectors. I really want to advocate for students especially, but for anybody using these tools, start off with something simple that you can control, and that's going to be offline data assimilation. And then, like I said, if time allows, I'll go into this interesting problem. So the world is all about machine learning these days and big data, so I'll at least have one slide where I express my ignorance on the subject. Yeah, as Takemasa said yesterday, Eugenia said yesterday, the problems in the geosciences are big, they're complex. That's why we're here. Other disciplines that are big and complex have a lot to learn from us. We've struggled with these problems for 50 years, and I think we've learned quite a bit over the course of that time. And the way I have experienced this, and I think the history of our field shows it, is that data assimilation involves knowledge of math and physics and using those to guide the solutions. And then the data comes second. The data comes in as part of the solution process. I think we know what it is that the data assimilation is doing, why it's doing it, and based on this background knowledge, how we can tune that. And again, my ignorance of machine learning, as I'm starting to get my feet wet with it, is mainly data first and data second. It really is being driven by the data. And there's sort of a proud agnostic approach about really not needing to know these things. And I'm not so sure that's the way to go, especially if you want to understand outcomes. Okay, so a little more motivation here. This is essential to making better forecasts, except perhaps when the forecast is being driven by boundary conditions. Data assimilation allows us to learn about the observations. And for weather and ocean applications, we understand these measurements fairly well. But for things like paleoclimate, we really don't. It involves geochemistry on biological organisms. And the relationships of the growth of those organisms to the climate system is really not well known, and data assimilation can help vet ideas for what might be happening there, what are called proxy system models. We also get to learn about the numerical models, how they work, their flaws. That's really the only thing we know for sure is that they're flawed, and so are the observations. And like I've been emphasizing, physical insight into the system, I think, is really important. And you become a well-rounded scientist by getting a healthy dose of fiber in your diet with probability, statistics, and computing. And by having access to these tools and these techniques, it allows you to move around more freely than I think most other people can. So I started out in traditional meteorology, and I'm doing paleoclimate now. My realm of interest has expanded over about 8 orders of magnitude in space and time. So I think it's fun to be able to do that. This is a slide I took out of a presentation I gave about 10 years ago at the University of Washington. It's called Math Across Campus, How Math Can Be Used to Solve Generic Problems. And I made this list, which I think overlapped really strongly with one that Takemasa showed yesterday. And really, you know, we've been thinking about this for a long time, but now it's almost everywhere. People are just getting models for systems that they didn't have access to before and measurements that they didn't have before. So that's exciting. In weather, the great curve shows us that the increase in skill in weather forecasting I regard as one of the greatest achievements in modern science that's benefited humanity. And this is due in part to an increase in the observations, especially satellite measurements, and our ability to forward model those measurements and use them in data assimilation. And of course, a steady improvement in data assimilation, which continues to this day. So we're looking over the course of decades, the increase in forecast skill, Northern Hemisphere and Southern Hemisphere, in different lead times. So we get longer lead times as we get to smaller skill here. But the anomaly correlations are going asymptotically to 1 here at short leads. Another really important thing that's come out of data assimilation is reanalysis, which provides us with a semi-consistent gridded data set over long periods of time. It's allowed us to do research that was not possible before that. For those of us that remember the pre-reanalysis era, it was kind of sketchy doing climate science, to do calculations on grids. It was difficult. There were limited resources. And now we have these wonderful data sets that provide us with comprehensive, dense in space and time gridded fields. And as I'll talk about today, we are now able to extend the concept of reanalysis back from the last 100 to 150 years back to about the last 2,000 years. And we're in the process of taking that back to the last glacial maximum. So it's exciting times in stretching data assimilation to longer timescales. For ocean data assimilation, we've really also had another revolution. It started about 10 plus years ago, where we started observing the ocean relatively comprehensively with the Argo floats. Nevertheless, we'd still like to know about very important things like the overturning circulation in the ocean, which is thought to be very important on decadal to centennial timescales. And unfortunately, it's very poorly constrained for anything but the last 10 years. Yes, Henry?
What's an Argo float?
An Argo float is basically it's a little porpoising tool that's instrumented, and it dives to depth in the ocean to about, depending on the float, 2 to 3 kilometers. So it takes a sounding, comes back up to the surface, has an antenna, transmits the data that it collected to a Iridium satellite, which is then downlinked to a base station. And so in real time, we have soundings of the ocean globally, everywhere except under the ice sheet in the Arctic. That's kind of all sorts of things. Temperature, salinity, I believe. I don't think they get motion from the floats, although it may be possible. They do have GPS, yeah, but I don't know if they have inertial systems that work. Yeah, so I'll show you a picture of what it looks like right now. So this is from 2 or 3 days ago. There are nearly 4,000 floats, right, that are doing this porpoising globally all throughout the ocean. So this has transformed our ability to resolve the ocean, which we didn't have the ability to do in the past. And that's become very clear when you look at, as Alicia Karspek and colleagues have done, look at the overturning circulation in the ocean. So the AMOC is the overturning circulation in the meridional plane in the ocean over the Atlantic basin. So we have high northern latitudes on the right, southern latitudes on the left, and this is the stream function. And so basically we have water subducting at high latitudes in the subarctic and the northern hemisphere, flowing equatorward. There's another return branch from the Antarctic at low latitudes. What I really want you to get from this is that these 6 on the left are all different reanalyses of this same quantity. And you can see that they're radically different. Some have local maxima where others have local minima. This would be analogous to not knowing what the mass overturning circulation is in the atmosphere, not knowing what the Hadley circulation looks like in the atmosphere. This is remarkable leading order uncertainty in the mean structure of the ocean. And it's fundamental to transporting mass and heat and salinity in the ocean. And we don't really know what it is. And on the right is a solution of the CCSM4 forced only by atmospheric boundary conditions. So the ocean is freely responding to surface fluxes from the atmosphere. The community-coupled climate model.
I think you ought to define the thing.
Thank you, Henry. I appreciate the call for clarification. Please keep me honest. I regret not being able to be here to return the favor. So if we look at the forced response, so this is basically doing the same thing with 4 other systems where we simply specify a known atmosphere and we look at how the ocean responds. They're much more similar. And in fact, if you compare those with the measurements we do have, so there is an instrument cable array near the Bahamas that's now measuring directly this poleward overturning circulation, and that's only been out there for about the past 10 years or so. That's given by this little black dashed line right here. You can see that those simulations that are just freely running and forced by the atmosphere actually match the data a lot better than those that have been given the data and had assimilation. So there's clearly a problem with the data assimilation approaches, and you could see it's essentially spaghetti as we go back into the past. That is, we really don't know what this overturning circulation was in the past. We can speculate about it, but the error bars are really wide. Okay? Huge opportunities here for data assimilation in the past. The future is much better now that we have these observations, but we still need to go back and make hindcasts. If we wish to make decadal forecasts and verify them, we can't wait 30 years to do that. Right? This is the benefit of weather prediction, is every day we get a lesson in how well we're doing. For decadal forecasts, we have to go into the past, which means we need better initial conditions and the ability to verify them.